Hi, now in this today's class we are going to look at the clamper circuit. Now what is clamper? A clamper is something that adds a DC voltage to the signals. Now suppose if I am having a AC signals and I add a DC voltage to AC signals. The output that I am going to get is just the superposition of this AC and the DC. Now what actually we are trying to do is to change the AC reference level of these AC signals. And by choosing a proper suitable DC voltage, we can shift the AC reference level to the positive side or else to the negative side. And the circuit that I used for shifting this AC reference level, we call it as a clamper circuit. Now there are two types of clamper circuit. The one that shifts the AC reference level to the positive side is called a positive clamper circuit, and the one that shifts the AC reference level to the negative side calls the negative clamper circuit. So in this today's class we are going to focus on the positive clamper circuit. Now here these are my input AC signals. Now this time the task is to clamp the entire AC signals to the positive side. Now to achieve this positive clamping, what we can do is that we can add the DC component to these AC signals, such that the superposition of AC and DC shifts these entire AC signals on the positive side. So let me take this AC signals. Let's see the circuit. Let this be the V input voltage, okay, that is our AC signals, and this time I'll be making a use of a capacitor C. Let this be the capacitor C, and I connect this capacitor to a diode D. Let this be the diode D, and we are going to measure the V out across the load RL. So let me connect the load RL across this diode D. Let RL be the load resistance, and we are going to measure the V out across this load resistance, plus, minus, and this is where we are going to measure the V out. Now while constructing this circuit, the important condition is the RLC time constant. Condition is that the RLC time constant should be made very, very large than the time period of input AC signal. So that's the important condition. You see that the RLC time constant is very large if you compare with the time period of these input signals. Now let's try to trace the output waveform. Okay, now here let's go with this time period from 0 to T/2. So the first case, from the time period is from 0 to T/2. That is the positive cycle. Now here the polarity, when it's in a positive cycle, this will become plus, minus, and here what we know, this is my P side and this is the N side of the diode. Now if you see this, plus is connected to the N side, that means the diode will be in the off mode, correct? So here I can say that the diode D is in the off state, or else a reversed bias mode. So let me draw the equivalent, the circuit diagram, how it will look like. So here this is my plus, and let this be my V in, and here that's the capacitor C. So here it will be open circuit, and we are measuring the V out across this load RL. So let me show this is a plus and minus, so where we are going to measure the V out. So this is the equivalent circuit for this time period, wherein the diode is in off state. And what we know is that the RLC time constant is very large. So for this time period, the capacitor won't charge fully. Okay, so here it will act like an open circuit like this. So the capacitor will charge through this load RL. Alright, so here if I show the load RL, so capacitor is charging through this load RL. Now during this time period, what we will observe is that the output, that follows the input. the capacitor is not fully charged. The capacitor is started charging through this load RL. So here the output will be available. The input will be available at the output. Okay, so that's the first positive cycle. Now let's go to the second time period region, where it is from T by 2 up till 3T by 4. Okay, so from T by 2 to 3T by 4. Now in this region, the polarity that's in a negative cycle, what we know is it's in a negative cycle. So the polarity will change, and this time this plus will become negative, this will become positive. Now if you see this P is connected to the plus, that means the diode can conduct. So the diode, I can say the diode D is in on mode. When the diode conduct, the current will start flowing in this circuit. All right, so let me show the equivalent. So here we have plus, this is the capacitor C, and then we have the diode which is in on state. So I can show it like this. This is a closed switch, right? It will act like a closed switch wherein we have a V in. So here this time the polarity is negative plus, all right, and we are measuring the V out over here, plus and minus V out, and let this be my load RL. Now here the current started flowing in this, that means the capacitor will get charged, right? So the capacitor gets charged up till what? Up till this maximum Vm. So from T by 2 up till this 3T by 4, the capacitor will start charging. So at 3T by 4, what will happen? The capacitor will charge to its maximum voltage. So this is plus and minus. All right. So here what I can show is that when you measure the V out, you are measuring the V out across the load RL. So the V out will be almost a flat line. And during this time period, what we know is that the capacitor is getting charged, right? So the capacitor is available with Vm plus and minus. Now once it crosses this region from 3T by 4, that's the third region, from the 3T by 4 to T, what happens is that if you just focus on this region from here up till this 3, let me shade this with the black, okay. Now during this region, that's the previous region from T by 2 up till 3T by 4, the capacitor is charged to the maximum voltage. All right, so the capacitor is already charged. Now if you look at this magnitude of this input AC signal for this region, okay, what you will find is that the magnitude has started decreasing, right? Has started decreasing. So here if you see, this is a plus sign, and this is a plus that will make this as a forward bias. But if you look at this now, this is plus and this is connected to the N side. So the capacitor will try to make this diode reverse biased. All right. Now when both are equal, the diode is in an on state. Okay, no problem. Once there is a slight decrease in the input side, the magnitude, okay, the capacitor will make this as a reversed biased. So here I can say the diode D will be in the reversed bias. So the diode D will be in the off state, okay, because the capacitor will store the maximum voltage Vm, okay, and we know that the RLC is very large. So the discharging time will be very large if we compare with the time period, input time period. So when it's in the off mode, what you will find is the equivalent circuit. So this is the capacitor, and you are having, this is the off circuit, and you are measuring the V out across this plus and minus. So this is the V out, and here this is my V in. So this is negative and positive, and what I know is negative plus negative. The capacitor is having negative Vm. All right. Now if you see this, the output what you are going to get is the whatever voltage that is available on the capacitor will be traced at the output, because this is acting like an off circuit. All right, and we know that the capacitor is having a maximum voltage of minus over here plus of minus Vm. Alright, so the output you are going to trace the voltage that is available over here. So what I can draw is, for this region, so the output what you are going to get is just the voltage that is available across the capacitor. Alright, now for this, the next positive half cycle, when you go, that is from 3 to 3t by 2. So the fourth region, 3 from t to 3t by 2. This is a positive cycle. Okay, now let me draw the equivalent. So this is my capacitor C, and it is already having some charge. Alright, and here this is my V input. This time the polarity will get changed. So here this negative will become plus, and plus will become negative. So let me change the polarity. So this time this will become negative. I'm having a V in, alright, and here we are going to measure the V out, plus, minus, and V out. Okay, so first, if you want the load, you can just show it, load RL. Alright, now if you see this for the first positive half cycle, okay, previous cycle it was in off state. Alright, now this plus is connected to the N side. Okay, that means the diode will be always in the reversed bias for this entire positive cycle. So what I can say is that the diode D is always reversed biased, for the positive cycle, In that case, now here if you apply the KVL, now let's apply the KVL. To get the output. Okay, now here there is a voltage rise. So what I get is V in. Even here there is a voltage rise. That's the voltage across the capacitor, which is equal to the maximum voltage Vm, and there is a V out. So if I apply the KVL, what I'm getting is V out is equal to V in plus Vm. Correct? So that's the expression what I am getting. Now with the help of this expression, I can trace the entire output waveform over here. Now see, when the V input, okay, let go to this point. When V input is equal to 0, let me write it here. When V input is equal to 0, if I substitute in this equation, what I get is a V out is equal to Vm. Correct? So that's the same point. If you see this at time period t, what you will get is this corresponding time. So this is my Vm. Alright, I'm getting that as a Vm. Now once I get to this point, that is the Vm, when I substitute the Vm, V input is equal to Vm, what I'll get is the V out is equal to Vm plus Vm, that is twice the Vm. Now that is happening at phi t by 4. So here for the phi t by 4, I'll get the voltage that will be equal to the twice the Vm. Okay, so this is the point, that's a twice the Vm. Okay, so this is a twice the Vm. Now once again at 3t by 2 it's coming to 0. So again when V input is equal to 0, so the output what you are going to get is the same as the at 3t by 2. Okay, that's the Vm. So here this is at the Vm. Now for the negative half cycle, when you substitute, okay, so for 7t by 4, this is exactly at the minus Vm. So when I substitute for the negative half cycle, that is V in is equal to minus Vm. In that case, what you will get when V in is equal to minus Vm, yeah, so that will be equal to 0. So V in minus Vm plus Vm, so V out will be equal to 0. Now for the 7 by 4 t, what you will get is the 0. So it will be something like this. And once again for at 2t, it's at 0. So when it's at 0, you will get a Vm. So you will get a waveform, something like this. And again for the rest all the cycles, what you will find is, the same pattern will be observed. So what you can get it at the repeated waveform you can see. Okay. Now if you look at this output waveform, what we have done is that we have managed to clamp the entire AC signals to the, the positive side. If you skip this, because this is the initial start wherein the circuit, the first capacitor has to charge. Okay. If you skip this part from 0 to up till this T, and if you look at for the steady state condition from here on, what you will find is that we have managed to clamp the entire AC signals to the positive side. So this is how we can do the positive clamping. Now here the role of the capacitor is, it's acting like a battery source of carrying the VM volts, and this DC voltage is been added to the AC signals so that we can superimpose and get the positive clamping of the input AC signals. So this is how the clamper circuit works. So now let's see what happens when we try to bias this positive clamper circuit with some potential difference of V volts. Now this is the same circuit that I'll be biasing now. Now there are two ways in which I can do the biasing. So let me go with the first way, wherein I will try to bias this circuit in such a way that this diode is already in the forward bias at the initial start. So here, to make this diode forward biased, what I have to do is that when I put up my DC source, you see that you are connecting the positive terminal to the P side and the negative terminal, let this be my over here, minus. Now if you see this circuit, the diode is already in the forward bias at the initial start. That means the capacitor will charge, and let me show it over here. So let me use a VB be the battery voltage or else a biasing voltage, and let's consider, just for the example, let's connect a 5-volt battery. Okay, let's connect a 5-volt battery. That means the capacitor will charge to the maximum value of this. So here the capacitor at the initial start, let me show a symbol VC for the capacitor voltage. That means the capacitor is charging initially at the 5 volts. Alright, now here VM let's consider to be of 15 volts and the minus VM also to be of 15 volts. Now let's try to trace the output waveform. Okay, now for the first positive half cycle, now what we know at the initial start only the capacitor is charged up till the 5 volts. Okay, now when the first positive cycle comes, so here it's a plus and this is a minus. If you see this, the plus is connected to the N side. That means the diode will be in the reversed biased mode. Alright, so when the diode is in the reversed bias mode, the diode D will be act like an open circuit. But now this time there is some VB voltage that is keeping this diode D in the forward bias. So we have to overcome that voltage, right? So then only the diode D will go into the off state. So here let me show the 5 volt on this. So let this be my 5 volts over here. Alright, now from 0 to T by 2, what I can say is that once this signals come, so here let me show the equivalent. So this is my capacitor C, and here this is plus and minus, so this is my V in. So what I know is the capacitor is already having a charge VC is equal to 5 volts, which is a barrier over here biasing voltage. And what we know is that the diode is in a conducting mode, right? So I'll show it like this. That's a diode in conducting, and we are interested in the V out over here. So suppose the V input is equal to 0. Okay, let's go with the V input is equal to 0. This is the case. Now when I give the plus and the minus, that is a positive cycle to this, once I can say that V input, okay, suppose the V input is greater than 0 volts, or else the V input plus the voltage across the capacitor, that is a VC, is greater than the barrier, the biasing voltage, then the diode will go in the off state. So the diode will go in the off state. Why? When Vin is greater than 0, if you see this, this is the plus and this is minus at the initial start when the capacitor will charge plus and minus. Now here also plus and minus. So that means the voltage that will be available to this N side of the diode will be a maximum, right? Once the V input is greater than 0. So here when V in is greater than 0, the diode will go to the off state. So the diode will be in the off state. And when the diode is in the off state, that means whatever voltage available at this point over here at the input will be available at the output. So when the V input is equal to 0 volts, so what I'll get is a 5 volts at the output. Okay, but once it's increases above this 0 volt, what you will find, the output follows the input. And suppose this is my 15. Okay, so here this is my 20 volt. So it will go up till here and T by 2. So this is my 5 volt. Okay, so the output follows the input. Output follows the input. Now for this time period from T by 2 up till 3T by 4, you will find that there is a change in the polarity. So let me change this polarity, negative, and this will plus. So again, if you see the equivalent, so this is my capacitor C, and this time the polarity has changed of the V input side. So this is my plus, and now if you see, this is negative and positive, so plus is connected to the P side. That means there are some chances that the diode can forward biased. All right, so here the V in, what you will find in this region, so this is plus and minus, we are interested in the V out. So has the V in, the magnitude, what I said, the V in plus Vc is greater than Vb, then the diode will be in the off state. Now here for the same condition, what is happening, we are going to the negative side. That means the V in will drop, right? So the V in will get drop, and when the V in get drops, there will be not enough voltage to make this diode into the off state. So the diode will go in the on state. All right, so the diode here I have shown, the diode will go in the on state. Diode will go in the on state, whereas this is the voltage that is available across the Vc was equal to 5 volts. Yes, Vc is equal to 5 volts. Now if you see this from T by 2 up till 3T by 4, it's touching to the minus Vm, that is a 15 volts. That means this is plus minus, so the diode D is in an on state. All right, the current will start flowing in this circuit. And what will happen, okay, in the previous, at the initial start, the capacitor voltage was of 5 volts. All right, now the capacitor voltage from 5 volt, it will charge to this V in up till the maximum minus Vm. So here when it charges, so what will happen to the capacitor voltage, it will get increased by Vm volt. So now the voltage across the capacitor will be equal to the 5 volts, that is the biasing voltage, Vb also you can put, plus there is a Vm voltage from the negative polarity. So there will be increase in the Vm, which is equal to 15 volts. So now if you see, the voltage that is available across the capacitor is 5 plus Vm. Okay, that is happening during this T by 2 up till 3T by 4, the capacitor is getting charged. But if you see, if you try to measure the V out across this, the diode across the load RL, what you will get is the flat line at the output. What you will get is the flat line at the output. And during this flat line, okay, you will see that the capacitor is charging to this voltage. All right. Now, for this region from 3T by 4 till 3. Now, what has happened during this cycle is that the capacitor Vc, the Vc voltage is now, let me write it as Vc is equal to 20 volts. So here the Vc is equal to 15 plus 5, so that has gone to 20 volts. All right, so capacitor voltage. Now, if you focus on this region from 3t by 4 till up till t, the magnitude of this input AC signals gets decreased, right? From 15 it will go to 14. So, but if you see this, that's the available for the negative cycle. But if you see this N side is connected to the capacitor and it's carrying a 20 volts. A slight decrease at the input, the magnitude, because this magnitude is getting added up with this biasing voltage. Yes, and then only this is making it forward biased. All right. Now here, once there is a slight decrease in the input voltage, okay, so what will happen? The capacitor voltage is a maximum 20 volt. So that will make this diode D into the reverse bias. So the diode will be in the off state. So the diode will go in the off state. And if I want to show the equivalent circuit diagram, what it will look like is, so you have a capacitor C. So this is my negative, again this is the positive. All right, and it will be open circuit. It will be open circuit, and here we are measuring the V out plus V out. So what is the available voltage? Vc is equal to how much? Why? Because this is a 20 volts and this is my V in. Now the output that we are going to get is the same as the voltage that is available at the capacitor. So the output, if I trace the output, what I'll get is, it will go and touch up till this time period t, it will go and touch to the 0 volt. Okay, it will go and touch till this 0 volt. That's the corresponding time period t. All right, now when you go back to the positive cycle, that is from t to 3t by 2. All right, so for that, from t to 3t by 2, what you will find, there is a change in the polarity. So this will become plus and this will become minus. All right, now what you know is the voltage available across the capacitor is 20 volts. All right, now here this plus, minus and plus and minus. So a slight change at the V input, this is already is in the reverse biased. Even if you give some extra positive supply to this N side, that will make this diode always in the reverse biased. So I can say that the diode for the positive cycle, here this is for positive cycle, the diode D will be always reverse biased. Always reverse biased. And when the reverse bias happens, so here the same I can redraw it, this is Vc, and this will continue to be in the off state. Okay, continue to be in the off state. So this is my V out and this is the V in. So this time the polarity has changed, plus, minus, and this is the same Vc, which is equal to 20 volts. Now, if you apply the KVL for this, okay, for this positive half cycle, what I'll get is the KVL. When I apply the KVL to get the V out, there is a voltage rise. Even this is carrying negative and positive. Voltage rise is equal to voltage drop. So the V out, again, it will be equal to V in plus voltage across the capacitor. Okay, voltage across the capacitor. Yeah, so what we know is the voltage across the capacitor. Voltage across the capacitor is what? The biasing voltage plus the voltage, of the negative input signal. Okay, so that will be coming as a Vm. So this is the voltage, available voltage. Vc is equal to Vb plus Vm. Now, if you see at t is equal to 0, let's plot the output waveform. At t is equal to, over here, the V in is equal to 0. So what I know is V in is equal to 0. When V in is equal to 0, that will be equal to the V out will be equal to Vc. So I can say that V out will be equal to voltage across the capacitor. And what is the voltage across the capacitor? It's a 20 volt. So I'm getting that has a 20 volt. If you see this, this is a 20 volts voltage across T. Now at 5T by 4, so it's coming to be a Vm, right? So when I substitute V input is equal to Vm, so Vm plus Vc. So when V in is equal to Vm, the output that you will get is Vm plus Vc. So Vc is 20 volts, 20 and Vm is my 15 volts. That means 35 volt will be available. So this is my 20 Vm. So Vm, this is 15. This is my 30 volts, and that means a 35 will be here somewhere. So I can shift this to the 35 volts. So that's the 35 volts. That's the for corresponding time t 5t by 4. Now again, once again it will come back to 0, so you will get the same as a 20 volts. So this is at a 20 volts. And for when you go for the negative, that is going to be a minus Vm. So when you substitute V input is equal to minus Vm. So let me write it. V input is equal to minus Vm. What you will get is V output will be what? V output will be equal to minus Vm plus Vc. So Vc is 20 minus 15, that will give me a 5 volts. So at 7t by 4, okay, what you will find is, it's coming and touching at the 0 volt, at the 5 volts, okay. So that is minus Vm is what? 15 plus voltage across a capacitor is 20, so that will give me a 5 volts. So that's coming to 5 volts. And like this, it will continue for the rest of the input signals. If you see this output waveform, what I can say is that we have managed to clamp, the negative peak of this input signal to the biasing voltage of some 5 volts. So that's all from this positive clamper circuit with the positive biasing voltage. Now let's see what happens when we do the negative biasing for this positive clamper circuit. Now this time what I'll do is that I'll change the battery connection such that the diode at the initial start is in a reversed biased. So I'm going to connect this diode to the negative, the P side to the negative terminal, and this is the plus sign. So that's a small slight change in the circuit. Now let's try to plot the output waveform. Okay, so let's focus on the first region. That's the first region from 0 to t by 2. So that is your positive half cycle. So during the positive half cycle, what we know, the polarity, that is my plus and minus. What we know, the diode is already in a reversed biased. If you see this plus is connected to the N side, that means the diode will be always in the reversed biased. Correct? So the diode will be in the reversed bias. So I can say the diode D will be in the off mode. Alright. So in this case, the equivalent circuit diagram. So the capacitor I am having C. So this is my plus, minus. So this is my V in. And I know that diode is in a reversed bias. That means I can show it open circuit. And we are measuring the V out, plus, minus, and V out across the load RL, which I am not showing. Okay, this is my V out. Alright, so what I can say is that at the output side, yeah, so all the input will be available at the V out. Okay, the capacitor will start charging. So here I can draw the V out follows the input. V out follows the input, exactly. Now for the next time period, that is from t by 2 up till 3t by 4. So here second we have from t by 2 to 3t by 4, that is for the negative cycle. The change in the polarity will get changed. So this will become negative, this will become positive. Now if you see the connections, and minus is connected to the N side, that means there are some chances of making this diode into the forward biased. But again here what we know is that barrier potential has increased just because of this VB, biasing voltage. So we need to overcome that barrier. So on the negative side, let me show the 5 volt battery. Let's take the biasing voltage to be of 5 volts, which is equal to VB. VB is equal to 5 volts. Now once this V input crosses this 5 volts, then the diode will start conducting. So let me write when V input when V input is greater than the biasing voltage, now here in this case I have taken a 5 volt as for example, then the diode will get into the on state, and the diode D is in the on mode, and I can redraw, okay, the equivalent circuit as this is my capacitor. So this time there is a change in the polarity, so this is plus, and now the diode will conduct, so I can show it like this, all right, and we are measuring the V out over here, plus minus, and this is V out. So again here there is a VB, right? So this is my VB. All right, now the V out we are going to get. Now the capacitor will start charge. The capacitor will get charged to some voltage. Let's say we call it as a VC. Let's call this as a VC, be the capacitor voltage, negative and positive. So it will charge to the VC. Now if I want to know what is the voltage across a capacitor, I can apply the KVL. I can apply the KVL. So here in this case, when I apply the KVL, what I'll get is there is a drop, V input, there is a rise, so voltage across a capacitor, and again voltage across, that is a biasing voltage, is equal to 0. So the voltage across a capacitor, if I'm interested, so VC will be equal to V in minus VB. That will be the available voltage across the capacitor. Okay, so VC here is equal to V input minus VB. So what I know is that when I reach at this time period 3T/4, so the V input is maximum, so I can say it will be a Vm minus voltage across, that's a biasing voltage. All right, yeah. Now let's see for the third region, that is from 3T/4 up till T. So the third region, 3T/4 to you are having up till T, correct? Now during this region, now what we know is that the capacitor is already having the Vm minus Vb, correct? So the capacitor has charged from plus, this is minus, and the voltage across a capacitor is Vm minus Vb. Yeah, in this case what will happen when you trace the V out, okay, across this over here, so you will get a flat line for this time period T/2 up till 3T/4. You will see that once you have to wait it for the barrier potential. So here what you will find for this time period, that is from T/2 up till this point, let me call this as a A point and this is my B. Okay, up till the A point the diode is in the off state. That means the output follows the input. So here we will get a output follows the input, but once it crosses, it's in the on mode and the current will start flowing in that. In that case, if you measure, the V out will be almost a flat line, so that will be something like this. So you will get a flat line up till 3T/4. Let me show up till 3T/4. Now we are working in this region. Okay, now if you look at this, the magnitude of the V input is getting decreased, right? It's getting decreased. And if you see, this capacitor is now acting like a battery source, having some DC voltage of Vm minus Vb. Now if suppose if I took Vm is equal to 15 minus the 5 volts, it will carry a 10 volts. So the voltage across a capacitor is of now 10 volts. Whereas when you go with this from this point C to the B, what you will find is that there is a decrease in the magnitude of the V input. All right, now here from 3T/2 T, if I draw the equivalent circuit diagram, so here, so this is, I'm already having my capacitor already charged, so this is negative and positive, this is my V in. All right, so here what I will find, the diode will go into the off state, and we are measuring the V out, plus, minus, and this is my V out. Now the diode is going in the off state. Why? Because the decrease in the magnitude at over here. Okay, now here this is negative and positive, correct? So this is negative and positive. There is already a reversed bias. That means the potential barrier has got increased, correct? And we are giving the maximum voltage of 15 volts. right? So if you apply the KVL, if you apply the KVL to this side, what I'm going to get is, let me apply the KVL. There is a voltage drop, so this is a minus V in, and there is a capacitor voltage, so there's a rise in a VC, and there is a drop, so this is my V out, and we are interested in the V out. So what V out, well, I'll get is V out will be equal to V input, okay, so this is a minus is equal to 0, and V out will be equal to minus V in plus VC, and which I can rewrite it as a V naught is equal to minus V in. What is the voltage across a capacitor? It's a Vm minus Vb, so that's my Vm minus Vb. Vm minus Vb. Now using this equation, if you try to plot this at the output side, what you will get is that, here this is my minus 15, right? So at this point it is my minus 15. So let me consider somewhere here it will be a minus 10 volt. Now from minus 15, this is getting it minus 15, and what I know is this, the overall voltage of the capacitor is 10 volts. So I can say the minus 15 volts. So just for example, okay, so the V out is equal to minus 15 plus 10 volts, that's the overall voltage of the capacitor. So that will give me of minus 5 volts, correct? So here that's a minus 5 volt I'm available. Now at minus 10 volt, just for example, this is minus 10 plus 10, that will give me a what? 0 voltage, right? So here if you trace the output waveform, and at t is equal to 0, when I substitute V input is equal to 0, 0 plus 10, that will give me a 10 volts. Now if you plot these points on the output, what you will get is, this is my 10. At t, I know the input signal is coming to be a 0. This is happening at time t. So 0, I'll get a 10. So at this point t, so you will be getting exactly like this. This is happening for 10 volts at time period t. That's the corresponding time period t. Now when you go for the positive half cycle again, what we know is that positive half cycle, if we go, correct, so the diode will be always in the reverse bias, because if you see in this time period, the capacitor is already having the plus sign, right? Plus is connected to the negative, that means the diode was in a reverse biased. Yes, the diode D is in the off mode, and it will continue to be in the off mode for this positive half cycle. All right, so in that case, what you will get is that output follows the input. Output follows the input. So again here, this is my 10 volts. So I have to give it to the 15 volts. So it will be a 25 volts. So the output follows the input, you will get it. So this is the output waveform, what you will trace. At phi t by 4, you will find that it's coming to be the maximum of 25 volts, and this is the for 3t by 2. Or else let me show this, the same output waveform, how I got. Okay, let me plot the, let me draw the equivalent circuit diagram for the region from T2. Let's go on the fourth region, that is from T to 3t by 2. So the region for T2, 3t by 2. Okay, so what we are having is a plus. This time the polarity is getting changed, plus, and here I'll be having a negative. So this is my V input, and we are already having a capacitor, and what is the voltage across the capacitor? Negative plus, like this, and we are interested in the V out. So here what we know, the diode is always in the open circuit, yeah, and this is the V out, plus and minus, and this is my V out. If you apply the KVL to this, what I get is, when I apply the KVL, if I apply the KVL to this circuit, there is a voltage rise, V input, again there is a voltage rise, voltage across a capacitor is equal to V out. So this is the equation for the output, yeah, and what we know is a VC. What is a VC? So VC, I can rewrite as a V out is equal to V in plus Vc is what? Vm minus Vb. So now again here in this expression, if you put V in is equal to 0, so let me show this. So here when V in is equal to 0, so what will happen to this expression? V in is equal to 0. It will be equal to Vm minus Vb, which is equal to, the V out will be equal to Vm minus Vb. And Vm minus Vb is what? 10 volts. 15 volts minus your 5 volts. So this is my Vm minus Vb over here, Vm minus Vb. So this is the point. Alright. So at t is equal to 0, I am getting this as the same point. No worries. At 5t by 4, that's the maximum Vm. This is my maximum Vm. So when I substitute V in is equal to Vm, my V out, what I'll get is Vm plus Vm minus Vb, and that is equal to twice the Vm minus Vb. Twice the Vm is how much? 15 into 2 is a 30, 30 minus 5, that is giving my of 25. So this point is my twice the Vm minus Vb. Alright, so that's the maximum I'm getting at the output. Same way again for when you go for V input is equal to 0, you will get, that's a Vb over here. Now when you go for the negative half cycle, that is at 7 by 40, you will find that it's a minus Vm. So when you substitute V input is equal to minus Vm, the output that you will get is V out is equal to minus Vm plus Vm minus Vb, and this will get cancelled. So the final you will be getting as a minus Vb. So which is exactly the same. Okay. So at 7t by 4, what I'll find is that the output you will be getting is at the minus Vb is equal to 5 volts. So this is the answer. Minus Vb, here that's a 2 Vm, Vm by 4. So that is obtained over here. Again, the things will go on continue, okay, with the other cycles as well. So here you will find that once again you will get this as that over here. So that it will continue. It will continue. So this is how it is going to continue for the rest of the cycle. Now if you see this output waveform, what I can say is that the negative peak of the input AC signal is been clamped to the biasing voltage that we selected in this circuit. So you can vary the clamping level by selecting a proper voltage in the circuit. So that's all from this positive clamper circuit, and in the next class we will see the negative clamper circuit. So thank you very much.